Good morning, all. In today's session of parallel programming, we will be moving on to the last topic where we're dealing with two sorting techniques. One is your quick sort, the other is your Radix sort, but this is using your dynamic parallelism. I'll just want to refresh you the procedure what we go for using your quick sort. Given a list of elements, you need to either arrange them in an ascending order or you go for arranging them in a descending order. That is what the sorting technique means. And you can choose your pivot element as the first element. You can go for choosing your pivot element as the middle element, and you can even go for choosing your pivot element as your last element. And once you decide your pivot element, you go for making use of two pointers. One is your I value, the other is your j, where one points to the starting location, the other points to the ending location. And you go for incrementing your I value based on a condition where the element here is less than your pivot. And here you decrement your j value when the element here is greater than the pivot element. And in this process, I value and j value will stop at some location. So if your I value is less than j, you just go for swapping a of I. I mean to say the array value of a of I and a of j. And in due course of incrementing I value and decrementing your j value, you may get a situation where I crosses the j location. In that case, you go for swapping the value or the element with your pivot element, right? So when you are doing this, when you are swapping your pivot element and the normal element of this, you will not swap this j and your pivot element. You get all the elements divided into two parts, where the elements left off side of your pivot element will be smaller, and the elements which are existing right side will be greater than the pivot element on. And all these elements you need to again go for applying the same quicksort procedure, and here also on the left side we apply the quicksort procedure. So that's the reason when you are normally writing a quicksort program, we go for using recursive functions. And we have already seen in dynamic parallelism, when we were dealing, the dynamic parallelism in CUDA is basically used for recursive functions, where you need to continuously call the same function. So this is just an idea provided to you because you are already aware of how do you perform a quicksort. But here we see how to perform a quicksort using dynamic parallelism. Now, if you go for normal CUDA programming without dynamic parallelism, for each of the kernel calls, CPU will generate call a function which is present on the device, and after it performs an operation for each recursive call, it will return the control to the CPU, and CPU has have to again call the same kernel launch. So when you are giving the control for each kernel launch to the CPU, the amount of data transfer between the CPU and the GPU increases, right? So to avoid that particular problem, they have gone for dynamic parallelism. What happens in dynamic parallelism is, once the CPU hands over the control to your GPU, the GPU has the flexibility of calling the same kernel function recursively. So CPU can call its function by itself. For that, we need to change the code, which we'll be seeing while we go for the programming part. This is what the dynamic parallelism. So if you could understand here, kernel A will launch your kernel B. This is done by the GPU, and once you finish your kernel B, check whether the kernel A has finished and you perform these operations recursively. If you want to see the programming part of this, we generally have two functions here. One is your global void quicksort, which is related to your device function. Means this is will be executed by your GPU. Though it is executed by the GPU, who will call this function? The CPU will take the responsibility of calling this function, right? And in between, you have to go for performing the partitions and apply the same quicksort procedure, right? So if you want to indicate to the system that this is a function which is to be recursively called by the GPU, not by the host, we go for preceding it with a keyword two underscores device and two underscores. So this indicates that this is a function which would be recursively called by your GPU function, and the remaining part of your program, wherever you think that I value is incremented and j value is incremented, the remaining part of the code would be same. Now, the next sorting technique which we'll be dealing in today's class is about your Radix sort. Here also I'll just brush up how the Radix sort would be done. Given the list of elements, you need to first of all identify what are the maximum number of digits that are available. So if you are given the list of values, and out of which the maximum number of digits in each of the value is 3. And if you are having a number which is of 2 digits, assume if it is 72, you will be preceding the value with a 0, so that the number of digits in that number will be 0. So if you could find any of the numerical value which is less than the maximum number of digits available, precede the value with a 0, and you all know if I go for replacing it with a 0 at the end, the value of it would be changed. That's the reason I'll prefix it with 0. So given the set of elements, you will be giving it like this, and we start with the least significant digit. So when you see the least significant digit values, you go for arranging them in an order. Arranging them in an order in the sense, first you write the element 0. So when I write the element 0, I will be writing the 720 value. Next, I'll go for writing what is the next digit here, 5. So next you go for writing the element of 5. So it is 355. The next value is 6. So it is 436. The next value is 7. And you have two values of 7 here. So whichever order you have already in the list, you put it in the same order. So 457 would be coming first, and then you have 657, and the next value would be 9, and in 9 329 value first, and then again 839. So you have sorted them based on the least significant digit. So next you go on to the next order. So when you see the order, the values are being changed. Now again you need to see these values. So you need to first get 2 value, then you need to get the 2 value here, then arrange your 3 values, next arrange your 5 values. So based on that only you could arrange them based on your second digit. And finally, we move on to the first digit, where we arrange based on your first digit. So when I see the first digit, which value will be coming first? 3 value. So it is 329 followed by 355. Next is 436. Next is 457. Next one would be 657 because the digit here is 6. And when I'm concentrating on a single digit, meaning that you go for swapping the total number. Next would be 720, and the last value would be 839. So this is a normal procedure for performing your Radix sort. And if you want to use CUDA programming, CUDA dynamic parallelism for this, and you see the number of kernel launches you are doing. So each time you need not go to the CPU and make a kernel launch, right? For each iteration, you can just call the device recursively. So for that, we go for using a template in CUDA, which we call it as a thrust. And thrust is a C++ template library, and using this template library, you need not write the code from the scratch. You have all the built-in functions available, and this is nothing but your high level language, where you not start writing your language from your low level code. You need not specify all the instructions at the low level. You can just use the built-in functions which are available. So let me first tell you what are the functions that are available. So if you want to go for storing the data at the CPU side, you go for host underscore vector, and for the GPU side it is device underscore vector. And if you want to perform the operations, just sort will sort the values parallelly, and reduce will perform the reduction process. And you can even go for data transfers, where you transfer the data from your host to device and device to host. So all the predefined functions will be just clubbing them and writing a program. Let me show you the example of writing a program here. For that, we have to include vector.h, device.h, and sort.h, and you go for generating normal data on the host. So it is host underscore vector. You are specifying that it is a integer value, and the host data capacity is 1024. And in the host data array, you are storing 1024 elements. It is not required. This is just the capacity. You can reduce the number and store the data. Now the data is available onto your host, right? Now you have to transfer the data to the device. So you have to just use trust device vector. Int is the data type, and device data. So from host data, the data is being transferred into your device, and my data is now readily available on the device. So I need to perform the sorting technique. So when you want to go for sort, it is device data dot begin. You are sorting it, and end. So these two functions will start your sorting process and stop it. And once you are done with your sorting process, you have to just transfer the data back to your host, right? So device data dot begin and device data dot end will indicate that you are starting the transfer of data back into your host, and you can go for printing the sorted data. So when you see, just to see the program, it is hardly a matter of 10 to 12 lines, where you are writing your built-in functions and completing your program. That is the main advantage of using your trust library. This is all about your fifth unit of CUDA programming, and this with this we wind up the syllabus of CUDA programming. Thank you all.